Rahim. Honorable assistant, salam alaikum. Donc, dans le cadre des soutenances des doctorants en informatique, on a aujourd'hui le doctorat de M. Jalal Hamouda dans l'intitulé New Technologies for Security and Privacy Issues in the Era of Industry 5.0. Donc, أولاً نرحب بأعضاء اللجنة على رأسهم الأستاذ صريدي لبت الدعوة من جامعة عنابة وباقي أعضاء اللجنة. Donc, tu as à peu près 30 minutes pour expliquer l'essentiel de ton travail. تفضل.
Assalamu alaikum. Thank you, Mr. President, the esteemed members of the jury, my supervisor, dear guests, family, and colleagues. Today, I have the honor of presenting my PhD defense about new technologies for security and privacy issues in the era of Industry 5, supervised by my mentor, Dr. Hamida Najat. So thank you all for your presence and support, and let's start. This is the outline of our presentation. As part one of state-of-the-art overview will be introducing Industry 5, architecture and its threat models. Then we move straight to our main research focus, which is the intrusion detection system, denoted as IDS, as a promising security solution. Following this, we'll be discussing IDS deployment challenges in Industry 5 as open issues and research objectives. The second part of our presentation will discuss our 3K proposition. So before introducing Industry 5, let's briefly overview the past industrial revolution. So the first one brought mechanization, the second brought electrification, the third one saw the rise of automation with the integration of electronics and computers, and recently Industry 4 brought digitalization, integrating advanced technologies such as the Internet of Things, artificial intelligence, and big data analytics to create the concept of smart factory, enhancing efficiency, reliability, and autonomy. Now, we stand at the threshold of Industry 5. This new era facilitates human intervention when necessary, integrating critical thinking, personalization, and adaptability into industrial processes. So this new era continues to deploy the advanced technologies seen in Industry 4 and further complements these advances by incorporating the human factor. So what is the whole purpose? Now, security and privacy concerns are increasingly critical in Industry 5, where vast networks of interconnected devices expand the potential attack surface and vulnerability to cyber threats. Also, personalization, which requires handling sensitive data, consequently raises significant privacy issues. Now, securing Industry 5 ecosystem necessitates protecting all its components, including cloud security, Internet of Things security, network security, against a wide range of cyber attacks. Here, we structured Industry 5 architecture into 4K layers, where each layer plays a vital role in ensuring the seamless operation and integration of advanced technologies. We also grouped the representation of all possible threat models that could compromise the security of Industry 5 in each layer. So the physical layer responsible for collecting and transmitting data and also performing actions based on received commands. Threats are data breach, data poisoning, and cyber attacks. And next, the middle layer, which acts as a bridge that ensures the seamless communication between the control and the physical layer. Possible threats are protocol exploitation, malware injection, and Byzantine attacks, and these were malicious nodes in the network send conflicting information to compromise the system. The control layer, and here where real-time automation and data processing resides. Threats are artificial intelligence vulnerabilities, malware injection, insider threats. And finally, the application layer that ensures the user-facing application to provide advanced functionalities and services, where threat models are data breach, malware injection, and external threats targeting the application layer through cyber attacks like ransomware, phishing, and SQL injection attacks, etc. So what are the security requirements and strategies for Industry 5? Here we outline this requirement based on 3K questions. The first one, what must be implemented? The second, what must be added? And the third one, what should be kept in mind? So the first one are security mechanisms, including strong cryptography, lightweight authentication and access control, and privacy preservation. The second are security tools, which is host-based, network-based, or hybrid tools. And the third one are security practices, like the security by design, implementation of communication protocol and control system, periodic evaluation, and security awareness. Our main research focus relies on this area, which is the intrusion detection system as a promising security solution that collects data from network traffic or systems and analyze it for any potential security breaches or imminent cyber attacks. Why we choose this area? Because it offers real-time threat detection, allowing immediate detection of potential cyber attacks, and also the protection of sensitive data by detecting any attempts of unauthorized access or attempts to alter the integrity of data. Also, it offers multi-layer security coverage and integration with other security measures for a holistic defense strategy. Finally, this tool offers adaptability to emerging threats where modern solutions like machine learning and behavior analysis could be used to adapt to new evolving cyber threats, enhancing protection in dynamic environments. Here we outline the challenges for the deployment of IDS in Industry 5 based on, according to the IDS taxonomy. For data source, IDS must handle heterogeneous and large-scale data, also the unbalanced and non-identically distributed data, and also the need for authentic datasets and test beds to ensure effective IDS training and evaluation. In terms of detection methodology, there is the frequent normal behavior, anomaly-based detection sensitivity. In system deployment, we have the resource constraint issues, which limits the availability of resources for implementing efficient IDS solution. In terms of performance, we have the escalation of false alarms and the accuracy vs real-time detection trade-off. In addition to this, there is the inherent security risks with the IDS solution itself, like the IDS must ensure the privacy of data they use to monitor and analyze, and must be robust against adversarial attacks that tries to evade detection, and also the challenge of zero-day attacks, which are unknown attacks, remains a challenge for the IDS. So each of these factors underscores the complex landscape of IDS deployment in modern Industry 5 environment. So our research objective is to provide an adaptive security monitoring IDS tailored to the security needs of Industry 5, and also to address the IDS challenges by integrating and consolidating new technologies. We aim to propose efficient and secure detection mechanisms that enhance privacy preservation, resilience, and reliability in Industry 5 security. Moving on to our proposition, the first one explores the application of federated learning in IDS for malware detection. Our objective here is to provide privacy-preserving and scalable malware detection, and also to address the privacy issues and computational overhead of IDS in a resource-constrained environment. For this, we propose the emergent federated learning paradigm for IDS training that ensures both data privacy and resource efficiency. We focused on Android malware detection due to the widespread of these open-source operating systems in industrial control environment, which makes them a prime target for cybercriminals injecting their malicious software. Here we outline a taxonomy of malware analysis techniques and detection strategies to outline our proposition, which adopts the novel dynamic analysis of malware based on the predictability of their network behavior. Also, as a host-based distributed approach for malware detection, focusing on privacy preservation, computation cost, and detection efficiency. Here is the flowchart of our proposed malware detection. Here, clients represents individual devices such as routers and firewalls that collect and analyze their own traffic data, and also collaborate to create the global model with collective threat intelligence and data privacy to identify malicious patterns of malware. They are chosen based on factors like data representation, device capabilities, and connectivity. So the process starts from any edge server node, who initialize the learning task, initializing the initial model and training parameter. Then he sent this information to the selected clients. The clients instead perform local model training and send back the updated to the server. The server instead aggregates these updates in a global model and then evaluate it on step 4 on a totally independent test dataset. If achieve the target accuracy, then the model will be deployed, else steps 2, 3, 4 will be repeated until model convergence or achieve desired model efficiency. In our implementation, we validate the performance of our proposed named federated CNN on the Android, adware, and general malware dataset benchmarked on 2017. This dataset includes hundreds of benign and malware apps, where the author tests these samples on smartphone executed user interaction scenarios and capturing malware network patterns and extracting 80 features. On the right is our experimental settings, where we compared our proposed here against the centralized alternative, employing the same CNN model architecture and training configuration. So here, a comparison of model accuracy, loss, and training time. Above is the centralized approach. The highest accuracy achieved here is 84%, and below is our proposed federated approach, which achieved comparable accuracy using 10 clients. Despite the accuracy drop with more clients, we achieved better training time. Above is the confusion matrix about our binary classification using both approaches. As we can see, we can determine achieving comparable results, and below is a performance comparison with other related approaches using the same dataset. One important thing here is that different studies use different strategies and number of training and test sample, and this is why we implemented the centralized approach as a baseline to propose a fair comparison with our approach. To recap, in this proposition, we explore the effectiveness of network-based and federated learning paradigm for malware detection, focusing on privacy preservation, computation cost, and detection efficiency. The results demonstrate achieving comparable results with the centralized approach. However, with limited detection accuracy related to network statistical features. Feature work and refinement will be incorporating diverse data sources for enhanced detection and also improving the federated learning-based IDS framework. In the second proposition, we explored blockchain application with federated learning as a privacy-preserving secure system for industrial Internet of Things, the core component of Industry 5. Our objective here is to address federated learning vulnerabilities, such as securing and enhancing privacy preservation of model sharing mechanisms, and also address the unreliability issues, such as the validity of shared models. We also aim to improve IDS performance by extending the federation scope to overcome data availability and resource restrictions. We also include both data dispersion mode in the evaluation of our proposed IDS. To achieve this, we proposed the innovative blockchain-enabled federated learning, mainly to incentivize the cross-silo or cross-organization federation based on cryptocurrency, and also by implementing a lightweight consensus protocol to optimize and secure the process of federated learning across untrusted participants. We differentiate our study from other related federated learning-based ideas in blockchain schemes by opting for new features like ledger distribution, fault tolerance, participation in consensus, smart contracts, model encryption, differential privacy, the proof of learning, and both data distribution modes. Here is the workflow of our proposed blockchain-enabled federated learning. So step 1 is task proposal. A task publisher initializes the learning task, setting rewards and outlining conditions for participation. This information is embedded in smart contract on the blockchain. Step 2 is investor application, placing a proof of eligibility and demonstrating their capacity to contribute to the federated learning process. In step 3, delegated investors are granted restricted access to the learning chain. Here, the learning chain is a blockchain-based ledger that used to manage the learning task. And in step 4, each investor could initialize the federated learning task. Here, step 5 and 6, each investor operates as a prover node who ensure secure and efficient aggregation using their associated clients, and then conceiving a new block once solving a proof of efficiency. once solving this proof, the prover provide and broadcast this block to validator nodes who acts as blockchain maintainers responsible for block addition. So here is an overview of our system component, starting from the edge clients, who proceed with a customized training procedure using the differential privacy stochastic gradient descent. Here it starts with computing gradients, when gradients, and then gradients, the gradient tipping, which involves scaling down gradients that exceed a certain threshold, which ensures that no single data point has too much influence on the model output. And also, after this, a noise determined by the desired level of privacy is added to the script gradient, which is controlled by a hyperparameter. And lastly is gradient descent update. A private node who initialized the initial model from the learning chain and send it to his associated clients, and then aggregate updates from these clients and evaluate a proof of accuracy or a proof of efficiency based on the latest proof recorded on the learning chain. Here is the structure of our proposed blockchain. And finally, validator nodes who validate the submitted new model containing blocks and achieving consensus. If so, the block is added to the learning chain. If not, the block is rejected. Here is our proposed consensus mechanism, named proof of federated learning. Here, when the prover generates and submits a new block to the leader node, here the leader node is one of validator nodes responsible for verifying the model and add it to the learning chain. Then the leader node retransmit this block to the validator nodes. The validator nodes here evaluate the model inside the block on a totally independent validation set. And then they reach consensus and confirm adding block to the leader. The leader, once receiving at least ND2 plus 1 confirm adding block, the block is stored on the learning chain. In our implementation, we validate the performance of our proposed framework on the Edge IoT dataset benchmarked on 2022. This dataset contains a realistic representation of industrial IoT environment with comprehensive feature set and diverse attack scenarios suitable for federated learning-based ideas. In our implementation, we evaluate both stages, where the first stage denoted the centralized federated learning managed by prover nodes. Here we explore a number of edge clients with dedicated data resources and associated to prover nodes, and also integrating differential privacy, both data distribution mode and employed metrics like accuracy, precision, detection rate, and time complexity. In the second stage, we implemented the consensus mechanism and explored a number of participating provers and employed metrics like energy cost, blockchain storage, and throughput. We compare our PPSS-enabled IDS efficiency and effectiveness with the centralized based federated learning IDS. Here is the per-class performance using different models and settings, as well as the performance compared with data distribution differential privacy settings. As we can see, we achieved 100% precision and accuracy for the normal traffic in all experiments, and also the federated aggregation effectively ensures transfer learning between participants with non-identically distributed data. However, for some classes like fingerprinting and ransomware attack, these are widely misclassified, and also the differential privacy negatively affected the overall attack recognition. Here, we can determine that federated learning shows limitation when data is inefficient. And this is a temporal evolution of global model accuracy with varying numbers of provers and clients. As we can see, both CFR and PPSS achieved comparable accuracy, which is 94%. Our approach achieved better accuracy with increased number of participating prover nodes. However, with differential privacy training, we can see that our approach outperforms the CFL in global model conversion time due to the fact that differential privacy training is computationally expensive, and our proposed use fewer training iteration but more model aggregation than the CFL. Here is the results which demonstrates the trade-off between data privacy and model performance. As we can see, the CFL performance decreased significantly with increased noise. Here is where epsilon is the introduced noise level, where smaller value indicates stronger privacy. However, our approach performance also decreased, but it was more resilient than the centralized federated learning approach. We can determine that our proposed offers better privacy protection than the CFL. Moving on to blockchain performance. Here the above table is the average data generation rate and storage overhead in the learning chain, where the average block size was 6.5 megabyte, when the maximum storage reached 51 megabyte, which makes them applicable to real-world permission blockchain at the top layer. And below is the average energy consumption of PBS-enabled decentralized federated learning tested on tested T4 GPU devices. We can see that differential privacy significantly increased the energy cost for both, but more for the CFL. And our proposed is more energy efficient due to the cost-effective model aggregation and also lower proof of learning consensus cost. To recap, in this contribution, we propose a novel security framework named PPSS for Industry 5, focusing on secure and privacy-enhanced federated learning for IDS, and also focus on expand the federation scope across untrusted parties to overcome data shortage. Our PPSS components are validator nodes who maintain the blockchain, prover nodes moderate the centralized or localized federated learning process, and edge client who engage in differential privacy-enhanced model training. We evaluate our proposal for cyber threat detection, and the result proven the security and integrity of model training process, effectiveness, efficiency of IDS against a wide range of cyber attacks. However, we determined that the cross-silo setting may degrade performance due to the different feature vectors and also challenges related to differential privacy and non-identical data distribution, which limits the effectiveness of federated learning detection models. In our third proposition, we explored a federated generative AI approach for enhanced and reliable cyber threat detection. Here we aim to address challenges related to IDS efficiency and robustness, specifically the unbalanced and non-identical distribution challenges, and also robustness against zero-day and adversarial evasion attacks. Zero-day attacks happens when the attacker exploit a known vulnerability to attack the system, consequently producing novel behaviors, making them difficult to detect and identify by the IDS. Adversarial evasion attacks are techniques that generate false data inputs to deceive classification models, where the attacker could leverage these techniques to implement complex attack, replicating adversarial examples' behavior to evade detection by the IDS classifier models. So in this approach, we leverage the federated learning with generative AI to ensure effective cyber threat detection in IoT resource-constrained environment, and propose a three-model paradigm using the conditional generative adversarial networks. We differentiate our study with other related GAN-based IDS approaches by opting for features like federated learning, adversarial defense, data augmentation, and application in IoT environment, also differential privacy, and the non-identical data distribution model. Our approach consists of a federated generative model, a discriminator model, and a classifier model. The federated generative model here learns to produce high quality and diverse data samples, consequently augmenting and improving the diversity of training data, handling unbalanced and non-identical data issues with and limit the risk of zero-day threats. The discriminator model learns how to differentiate between real and synthetic samples, and proving its ability to discern and classify adversarial attacks effectively, and also providing a feedback to the generator to produce high-quality samples that resemble the real data. And finally, the classifier model here trains on a large and diverse data set, consequently identifies a wide range of attack classes and also improving robustness against zero-day threats and when manipulated with adversarial attempts. So here we started with C-GAN training under the federated learning setting, where the generator is shared between clients while the disseminator resides on the client side. This setup aims to enhance privacy preservation, stability, and efficiency of distributed GAN training. Next, we train the global classifier under the federated learning settings, where the classifier is shared between clients and influenced by augmented data rather than only relying on local updates contributed by individual participants. We also introduced the differential privacy training to the classifier model and evaluate how augmented data in synthetic federated learning actually alleviate the negative effects of differential privacy. In our implementation, we evaluated our proposed approach on the same dataset. On the right is a flowchart outlining the model training, aggregation, and evaluation. We started here with distributing the train set across 10 clients. Then we proceed with federated GAN training, once model conversions. And here in this step, we proposed also a data refinement approach to align the generated data with the original network traffic data boundaries. And then next, we train the classifier model influenced by the augmented data and evaluate it on a separate test set. Here we also evaluate the individual discriminator models against adversarial attacks. This is the local training laws of federated GAN training using the Wasserstein distance with the differential gradient with the gradient penalty. There is a noticeable convergence pattern here where the losses of both models approach each other, suggesting a stabilization in the adversarial dynamics between the both components of GAN. And here is an examination of validation accuracy in our federated generative approach compared to the standalone federated approach. Our approach demonstrates higher efficiency and nearly equivalent to the standalone federated approach without differential privacy training. However, with differential privacy training, our approach surpasses the standalone approach when differential privacy is integrated, highlighting its potential as a cost-effective, privacy-preserving solution. We can determine that this combination of our approach with differential privacy training significantly enhances privacy protection and mitigating the negative impacts on model performance. Here we evaluated the robustness of our approach on two test sets, the original one and the other augmented test set, which introduced new attack samples to simulate zero-day attacks and expand the test data coverage. Our approach maintains higher accuracy than standalone across both datasets, and also our approach outperforms the standalone approach by 10 to 14% in the augmented test set under both privacy conditions. Here the results shows the effectiveness of our approach in the context of zero-day attacks. We can see that our approach is capable to identify unknown attacks accurately, thereby reducing the risk of undetected attacks. And this is primarily attributed to our data augmentation techniques. And below is performance comparison of proposed individual detectors against 3 evaluated adversarial attacks. We can see that the results here vary significantly among clients. However, the additional classifier enhances detection of undetected adversarial inputs, consequently boosting adversarial system robustness. So to recap, in this proposition, we propose 3-model paradigm, leveraging the generative AI with federated learning, focusing on addressing unbalanced and distributed data, and also enhancing resilience and robustness against zero-day and adversarial attacks. Also, this approach uses the conditional GAN to generate high-quality and diversified IDS data, addressing distributed data challenges, and a federated learning approach that uses this generated data to enhance detection efficiency and resilience against zero-day attacks. However, secure aggregation and authentication of model sharing are still required to ensure the integrity and trustworthiness of our framework. In conclusion, in this work, we emphasize the importance of innovative detection strategies to counter large-scale cyber attacks and also successfully balance the demands of emerging technologies with the security and privacy concerns in Industry 5. For future work, we aim to explore alternative privacy protection measures such as the homomorphic encryption and enhance generative model capabilities through self-supervised learning methodologies. Thank you for your attention, and final word to Dr. Mohammed Amin Farag for his unwavering support and guidance throughout the realization of this project.